Welcome to Machine Learning on the Edge. My name is Zach Shelby, co-founder and CEO of Edge Impulse. Data and machine learning are having a huge impact on all industries: medical, industrial, logistics, energy, you name it, thanks to advances in edge computing. On this show, we bring you the latest insights from business and technology leaders working with machine learning. I'm here with Steve Kent, Chief Product Officer of No Labs, who makes non-invasive glucose solutions, former head of science at Aura, and the founder and CEO of medical device company Invicta Medical. Steve, welcome to the show.
Thanks for having me, Zach. Great to be here.
So I always like to talk with people about their own motivation history getting involved with technology and data and machine learning. Yours is super fascinating. So tell me about how you got interested in medical and devices as a thing.
Yeah, it's pretty amazing because growing up, like the way that my dad and I would spend time together was taking apart electronics and new computer chips in our garage. And he worked in advanced supercomputer systems and medical devices as well. And him bringing this technology home and basically giving me some goggles and a hammer and letting me have at silicon wafers, most of the chips that you actually see at the Intel Museum. Of course, these were components that were at the time damaged and not fit for use, but as a child, being able to open those up and really see the power that technology enabled in so many cool form factors. And then over the course of my life, seeing those be deployed across the internet, the development of the internet, and so many other devices, it's pretty remarkable to be able to see that come to life. So,
yeah, we were laughing once about this difference between mechanical engineers and electrical engineers. When you got the silicon wafers home, what did you do?
I hit them with a hammer. Yeah. Well, and if you look at the wafer, it has been etched, and it has been etched in a way that, the wafers are supposed to be analyzed and then broken on the vias so that you can put them into a chip. But if you hit it with a hammer, you get to see very interesting things happen. So
and I would have done the opposite. I would have been like injecting very fine signals into the pins on the chip to see what happens, right, digitally. That's, I think, what makes a mechanical engineer. You're not scared to break stuff apart and see how it works.
No, and it's the fun of trying to put it back together in a new way.
So, that brings us to digital health, right? Like, you become one of the most respected digital health innovators. How does a mechanical engineer get into digital health, right? What was your journey to go from breaking apart things as a child to working on data and machine learning?
Yeah, so kind of the fun of being an entrepreneur is it's your job to break things and rebuild them. So I think the approach has stayed true the entire time. But I actually got my career started as a medical device manufacturing engineer, doing advanced electrosurgical tool system design, development. And in that role, I had a few opportunities to come up with a really groundbreaking technology. But my actual position was as a consultant for an OEM firm designing these technologies for much larger organizations, some of the biggest in the world. And for me, it was this very interesting experience where we would have major technological breakthroughs and I would pitch. And then subsequently, I would be told that that's great. We'll launch that over the next 10 or 20 years through 6 or 8 different small iterations to get to that point. And I had this deep sense of frustration in those moments because my biggest goal in my career was to make the largest positive impact in human health possible. And it felt like we weren't doing justice to the patients and customers that deserve the best that technology can offer. So after this sort of frustrating experience happening several times, I decided that I had to start my own company so that I could use technology for what it was meant to do, which is transform the way that we provide care for patients and customers.
And that sounds like a disruption point for me. That's something I learned doing a few of these startups, that oftentimes it's this wall of frustration that you run up against working on something. For me, it was the Internet of Things back in the early 2000s. We were working on it, we'd solved it, we'd built it, and the big corporations were not interested. handed it to them on a platter, like, hey, you do this and this and this, can change the world. We network all devices and things. Yeah, not interested. Maybe in 15 years.
Yeah.
It sounds very similar, right? So how did that direct you to solving the problem that you solved in your first startup? Like, how did that disruption point, like, bring you down that path of working on this specific medical device? And how long does that take? I think that's something interesting for our listeners. Like, what does it take to build a medical device?
It takes a lot, and I don't think I fully realized how much it would take when I first started. And maybe that was the secret to diving in, is a little bit of naivete, thinking, yeah, we're going to solve it and it's going to work immediately and we're going to get to market. But you soon learn that it takes an enormous amount of clinical development and R&D and following very strict validation protocols and design, development, clinical testing, data collection, algorithm development, and so on and so forth. But that's all extremely important because you need to ensure that the devices that you're designing are meeting their intended function. But getting to that specific technology was actually a really exciting experience for me because I was working on advanced electrosurgical tools. So using high frequency energy to create plasma inside the body to essentially dissolve human tissue 1 millimeter at a time. So very good for joint surgeries and things like that we're using minimally invasive processes. So I had a really good understanding of how to use electricity in the human body. And then from earlier projects, I had worked in the sleep space for many years. So I was looking for what are the biggest problems that patients and customers experience in the sleep industry. And it was brought to my attention by one of my mentors that I had worked for in high school, actually at SRI International in the sleep lab. And I had lunch with him, and I just asked him directly. I was like, what's the biggest problem that you face in sleep today? He's like, oh, sleep apnea is the single biggest issue. And there's really no good devices to tackle that. There are effective devices like CPAP, but not very user-friendly, I think, as we all know, if anyone has used them. So in that moment, I very coincidentally, and this is sort of that spark that brings everything together, I had thrown my back out, and I was wearing an electrical stimulation non-invasive unit on my back. And at lunch, I actually pulled it apart, and this is the mechanical engineer break things. I was like, energy on my back, energy in the body, controlling your nervous system. I took it apart and put it on the chopsticks that I was eating lunch with and started poking around in my upper airway. And I found these locations that would dilate the muscles of my airway with e-stim. And that was the genesis of, interesting, there's something that we can do with electricity here. And there may be an easier way to do that non-invasively than we had previously thought. So very much breaking things and putting them back together.
The chopstick story is amazing.
Yeah.
But that brings us to digital, right? We've been on quite a journey together using data to solve health algorithm problems. And we've worked on dozens of clinical algorithm projects.
At least.
At least. It's been a really amazing journey. Data is really interesting in the space of digital health because it seems like although we do a lot of validation, data gets neglected as a tool to develop and engineer.
Right.
What does it take to succeed with data in big clinical algorithm projects and bringing an algorithm to market on a health or medical device? And like, what's the state of the art that people typically have when they haven't been using data?
Well, to answer the first part of your question, what does it take? It actually takes a very straightforward approach. And, I think you hear the term nowadays of, and we have for years, which is big data. It's like the answers will come from the information that we're gathering. Let's look at all of it. Mm-hmm. And in the case of clinical algorithm development, we found through many of our projects that if you actually focus in on very tightly controlled clinical experiments, collecting the highest resolution data sets possible in multimodal sensing systems, from that you can actually build a very clear correlations to your physiological systems that your sensors are picking up. So that's sort of like the bucket number one of organizing your sensors in a way and organizing and really focusing on getting started with smaller data. And then the second piece comes into when you think about how do I launch this successfully into the market to customers? Well, you need to understand all of your individual customer groups. So is your population predominantly male? Is it predominantly female? Is it blended? What age ranges are you looking for? What body types? What socioeconomic backgrounds? And historically, clinical trials have not done the best job at thinking about algorithm design from an equitable perspective. And I think one of the reasons why we've always been so successful in our work and in many of the projects we've worked on together is we think about the whole human. So the whole human and how that human fits into the social fabric that they're operating in. So by the time we've collected all of this information, we can provide them with very generalized data to this use case.
And that brings us to ground truth. Yeah. And I think that's really interesting in how data works, right? We're really trying to approximate really expensive lab sensors with cheap sensors to detect something similar. And so with sleep, right, it is the sleep laboratory with 30 sensors hooked up to your body. If anybody's done a sleep night in a lab, pretty uncomfortable, hard to sleep with all that hooked up.
Definitely not a normal sleeping environment.
Not a normal sleeping environment. And then a trained professional will score that sleep based on sleep stages, get an EDF.
Yep.
And that serves as a ground truth versus the cheap sensors, right? Things that we wear on our body that might measure things that could cost, $100 or a few $100s. And then we use machine learning to approximate that ground truth with the sensor data that we have.
Yeah.
But what's the real limitation of ground truth, right? How do you think of that as the medical device expert? What does ground truth give us, and how important is that to the medical community and to the digital health companies?
Yeah. So it's sort of like that. First and foremost, I must say that I'm extremely grateful for all of the work that goes into creating these ground truths, because a lot of the work that I do just wouldn't be possible if all of that historic work hadn't been done. So it's kind of a luxurious position to be standing on the shoulders of giants and looking back with hindsight and say, oh, that's interesting that this is the reference in that way. And I think about sleep staging, for example. Sleep is classified into these different stages, REM sleep, deep sleep, light sleep. And one of the original designers of sleep staging, he created that structure by dropping weights on people while they were sleeping to see when they would wake up. So deep sleep meant if I dropped a heavier ball on you, you would not wake up out of sleep. So, we have to respect what we have. And then from that, you can also look deeper into the status of those reference tools. And over time, as all of these systems evolve, we're finding new ways to think about the reference systems themselves and hopefully be creating the next class of them.
Yeah. And the reality is you can only be as accurate as your ground truth labeled in any data-driven machine learning system. So if your maximum accuracy for sleep scoring is 80%, your machine learning based sleep scoring algorithm, doesn't matter how much data you have, will never pass 80% in accuracy.
Yeah.
And that's a very interesting thing to think about then. Okay, great. We can start with the ground truth that we have today. Might there be more accurate ways in a laboratory to determine really how you're sleeping, what stage of sleep you're in? Could we get much closer to 100% in that ground truth, and then design sleep algorithms to match that? That's really interesting, right? So once we get to the state of the art, how can we go beyond it?
Absolutely. And we all have to remember that when you're developing medical systems or anything that will be used in a clinical setting, so many of the clinical decision-making algorithms that physicians and care providers use around the world today are based on very well-studied inputs. So you have to be thoughtful in how you introduce new solutions and also what that means, because the current clinical practices are well-studied and robust, which is why they usually lead to diagnoses and certain types of prescriptions. But that doesn't mean that it doesn't need innovation. And especially when you think of what technology allows, like new sensor innovation, taking what could previously only be done in a lab, a very expensive setting, technicians, all these wires. Yes, you're getting high quality in-lab data, but that's not your normal sleep at home. And it begs the question of, is that actually your sleep? Like, are we really getting even a good measure of that individual sleep? So
I sure slept badly when I was in the sleep.
yeah, I've done a lot of them, and it's not fun. So then when you think about collecting really high quality sensor data in the home in a normal setting over many, many, many days on a single individual, you get much more insight into what that person's physiological system is doing over time. And I think that allows us to ask new questions.
Yeah.
What is important to be measured? What makes them feel well rested or energetic, which previously you just can't do in one day. It's accurate, but you can't do that in one day.
You said something else that was really interesting, that you need this progressive approach to data collection and algorithm. Yeah. And I want to dive into that a bit more, because I think that's really important. Many people think that when we go and design these algorithms, we're building the biggest data set in the world of sleep, for example. Yeah. And then we magically, drive some machine learning wizards to come up with this algorithm. But the approach that we've seen work is totally different, right? Like, how much data is enough to go stage by stage into that process? Are we talking about 10, 100, 1,000 nights of sleep, for example, to get started? And then what do you want to validate in between?
Well, you have to get started somewhere. I would say if you're collecting, even on the order of 10 or 30 nights on a number of different individuals. Every human is slightly different from another, and they're not only different from each other, but every individual is different from each day to the next.
Yeah.
So trying to think of that profile, but the sample sizes are smaller than you think to get an early look.
N equals 10, N equals 30, N equals 50, 100, something like that to incrementally.
Yeah, and the process of developing any new technology, in my opinion, is in the spirit of learning. So if you're really pushing yourself to understand a new experiment and a new suite of sensors, you really need to dig into deep details on the technical side and understand, how do you optimize signal to noise, where is the most meaningful information coming from, and really understanding even down to your clinical setup. Did we set up the reference devices properly? Did we onboard the participants properly? Your clinical workflow. And good clinical operations can determine the success of your data quality. So I think starting small and really mastering the process will allow you to figure out where to invest your time and energy. And if you do that too soon, you could make a pretty big strategic error.
And this is expensive stuff.
Oh yeah.
Right? When you do one night we're just using sleep as an example. This could be anything, but one night of sleep in a laboratory, $1,000.
Yeah.
So you start multiplying that. If you get too far down that road and your sensors were wrong, your reference was wrong, your quality control process was wrong, you could waste huge amounts of money if you don't get that right. So that's where that incremental process is also much faster and much more efficient.
Absolutely. Yeah, you do not want to overinvest too soon. And that's kind of the general theme, I think, in entrepreneurship is, be careful with how married you are to your idea. It's like, be open-minded and try to problem solve along the way, because you might also find a creative way to collect the data or to enhance your clinical workflow that could make it less expensive. Or you understand that the reference devices are performing in certain participants better than others. Mm-hmm. So figuring that out early before you make those big investments is critical.
So Steve, we've been talking about some pretty cool sensors. We've worked on all types of exotic sensors, PPG, ECG, EEG, skin temperature. I'm sure you have a list much longer than me. Now you're working on something really amazing around glucose. So tell us more about your mission at No Labs and what you're doing in glucose and what kind of sensor is involved to achieve non-invasive glucose.
So the mission is clear. It is to provide the world's first FDA-approved, truly non-invasive glucose monitor to the billions of people who are suffering from type 1, type 2, prediabetes, and general metabolic health disorders, which are growing at an untenable pace for society today. So it is an enormous problem to solve, and so many companies have tried unsuccessfully until now. And so much of it is due to the fact that we have developed the first radio frequency dielectric sensor. And we're able to put this incredible non-invasive energy into the human tissue stack and measure the response. And it turns out that this sensor can hone in on blood glucose and provide us with, in our lab today, what appears to be a very promising signal.
So this sounds a lot like Star Trek and the tricorder, right? You go to a new alien planet, you see this thing, right? You don't know what it is. Is it a rock or a tree or a life form? And you stick the tricorder next to it and it scans it, right? And tells you what it is. It sounds very similar. So how does a bio RFID sensor work in practice?
Yeah, so it fundamentally uses the radio frequency and microwave frequency bands of the electromagnetic spectrum. Mm-hmm. And as opposed to visible light, there are many orders of magnitude more frequencies to work with in those bands. Mm-hmm. So we actually have a sensor that has a sensing element and a radio frequency projecting element. And from the projecting element, we can introduce 400,000 frequencies programmatically into the space above the sensing element. And then from that, measure the interaction with all of the molecules above it. So it really is creating this. It almost feels like magic. It's quite incredible, but you could imagine working with the first LEDs when they were invented. It would feel like magic as well in the early days of photonics. So actually quite similar concepts, but on a very different and I would say richer data end of the spectrum, because there's so much more information within radio frequency than there is in photonics.
And how do you think of glucose in that sense? Like we can detect glucose as a molecule with a sensor like this inside of your body tissues. Is it only glucose?
So right now we believe it's many different analytes, and technically the sensor is measuring anything above it. So in talking about our data collection methods earlier, our data collections are very much focused on getting really clear reference data against blood glucose from a variety of gold standard reference labels, and then building machine learning algorithms from our sensor to correlate to that. And in our lab, that's been quite successful. But it doesn't stop there. We believe that there are potentially up to 100 different analytes that we could measure in the human body that are of high value to the human experience and improving health outcomes.
And we've talked about the importance of the reference sensing quality, right?
Yeah.
The ground truth quality in the laboratory. But let's talk about the quality of sensors, right? What is the quality of the sensors that you're working with on the health medical device, the cheaper sensors? How does that impact, right, your ability to build an algorithm?
Yeah. Well, they're still today, lab analyzers are very expensive. The best gold standard in-lab analyzers are anywhere between $30,000 and $50,000, and that's not including a clinical team to run and operate that. It also requires a blood draw from your veins. So we will have people draw blood from a venous line every 5 minutes, put that into the analyzer, and that creates what the FDA would consider a gold standard reference label. But there are other technologies like continuous glucose monitors, which are less accurate than venous blood detection, but more wearable and continuous, as the name suggests. And then, of course, there are finger sticks where you actually prick your finger and draw a small amount of blood. The issue is that those are really painful. Those have been the standard of care for ages, but there's a reason why diabetes monitoring is still an issue, and it's because every other tool is invasive. You have to draw blood or fluid from the patient to get your reading.
And you're seeing success of this now because of the quality of the sensor that you've been able to develop.
That's right.
Where's that failed before, right? Like, how is sensing improved so that we're able to solve this kind of new health problem non-invasively?
Yeah, sensing has improved from our perspective and in our technology portfolio. It's improved dramatically. We actually have counted in the industry, and 88 different companies have developed technology to try to solve and do non-invasive blood glucose monitoring, but none of them have had the level of technical success that we have. And one of the reasons I think for that is many of them were trying to use existing technologies applied in a different way.
Yeah.
And that is a great way to solve problems. I think there's so many opportunities in healthcare to apply existing technology in new and unique ways to improve health outcomes. But in this specific case, it required a pretty dramatic technological breakthrough. And we know this quite well because we started in the very early days of no labs looking at optical-based sensors for non-invasive blood glucose. We tried that first. And I think the difference between our technical team and others is when we ran into those roadblocks, we didn't overcommit and try to keep forging that path with these existing sensors. We realized that, it's probably not going to work and we need to think of something new. And that created this beautiful innovation path, which has led us to the development of our radio frequency dielectric sensor today.
Amazing journey.
Yeah.
As an entrepreneur, you and I both know that's one of the scariest and one of the most rewarding journeys that you can have in technology. When you think about digital health and machine learning, right, we talked about some of the things that we've been doing and are doing right now, right, to apply data and machine learning to solve these new algorithmic problems, sometimes with exotic new sensors. Where's the value going forward for young entrepreneurs who want to get involved with medical devices or health devices like you? What should they be working on?
Oh, wow. We could talk about this all day. There's so much opportunity to make a positive impact in the world through technology applied to human health. So sort of zooming out and then zooming back in on the very high level, if we look at the last 5 and 10 years, we're seeing this migration of really advanced sensor development and continuous sensors being applied to health applications. And then those applications and sensor suite being put into the home for continuous use anywhere in the world. So we're seeing this transition of what was previously only available to be done in a hospital. You can do these tests and these experiments and these clinical data collections in the comfort of your own home any day. So that's happening. And we're going to see so much more of that as what I would say the real driver in healthcare, preventive healthcare, healthcare at home, is empowering individual patients and customers who may not be sick yet with the tools that they need to maintain their health. And then on the more clinical side of things, you're going to see major trends in workflow optimization and really helping support physicians with their existing workflows because we have a shortage of doctors, physicians are burned out. My partner, who's a physician, undergoes a huge amount of stress and really wishes that she could see more patients than she can today. So thinking about how to increase the impact of existing processes and staff. So I think it's this balance where you see these shifts. And I think technology and sensors is one of the best ways to do that because that's how you truly scale.
Amazing. Steve, thank you for being on the show.
Thanks for having me.
Great having you. Thank you all for joining us for this episode of Machine Learning on the Edge. We're on a mission to bring you the latest insights from business and technology leaders. So please join us next time.